Hello, everyone. Welcome to Temporal Graphs reading group on today, March 28th. And yes, so today we are glad to have uh, Jacob here, who will be presenting their recent work, Anomaly Detection in Continuous Time Temporal Provenance Graphs, which was also presented at the Temporal Graph Learning Workshop at NeurIPS 2023. And so more background about Jacob. So Jakub Reha is a PhD candidate at the AM Lab at the University of Amsterdam. He holds a bachelor's degree from the Technical University of Denmark and a master's degree from KTH Royal Institute of Technology. His research interests are centered around anomaly detection in temporal graphs and causality in machine learning, uh, specifically causal discovery in time series. So I will hand the mic to you, Jacob, and yeah.
Yeah, okay. Yeah, thanks for the introduction. So again, my name is Jakub, and yeah, I'm here to present our work, Anomaly Detection in Continuous Time Temporal Provenance Graphs, which was accepted to the Temporal Graph Learning Workshop at NeurIPS last year. And it was a joint work that I did in collaboration with people from Huawei during my internship there. And so there's Giulio, Michele, and Klaas from Huawei, and then Alessio from University of Pisa. And this paper is more application oriented. Oops. Right. And so the motivation for this work was the ubiquitous presence of cyber attacks. As you all know, I guess they are increasingly prevalent all around us in the society, and they cause serious damage. And so we would like to detect them. And the current literature on this is very limited, as they usually assume very limited scenarios where they, for example, discard temporal information, or they detect the cyber attacks on very coarse level of time. So, for example, they can say, okay, there was a cyber attack within this hour or during this day, but we want to be more fine-grained. And yes, so the goal of the project was to learn the behavior of the computer system from provenance graphs, which I'll explain what that is in a second, and then pinpoint these cyber attacks as anomalies in these graphs. And so while doing so, we also released two labeled datasets for this problem, and we adapted and evaluated the TGN architecture for this setting. Right. Yes, so provenance graphs are graphs that basically describe the behavior or the information flow in a computer system, and they are usually constructed from audit logs that are collected on this computer system. And these audit logs, they can vary in their format. So yeah, there can be different types of provenance graphs. But here I have an example, a simplified example. And yeah, we basically assume three types of nodes. So files, processes, and sockets. And then we have also different edge types. And these different edge types, they correspond to system calls on Linux machine. Yeah, and so we also label the edges as malicious or benign. And so this setting is streaming because the graph is always evolving over time, right? And so there are so-called events, which basically consist of the two nodes, right? And the edge type, the time step, and the edge features. And there are also node types associated to these nodes, but yeah. Yes, and so this is not necessarily connected to provenance graph, but we label the cyber attacks as edges. So we will work on the edge level. And so in this specific example here, yeah, you can see that the red edges are malicious, right? So there is a cyber attack which starts here at the top. And so basically there is a virus infecting through the browser. It infects the password manager, and then it reads some passwords from the password file .dat, and then through several steps, it exfiltrates these passwords to another foreign IP address. Right. And so we introduce two new datasets, which we call trace and Thea. And the duration of the data that was collected was 10 days. And there are in total 6 cyber attacks. So there are 4 in trace and 2 in Thea. And in total, so there are 262 malicious edges in trace and 211 malicious edges in Thea, which means that the datasets are very imbalanced because there are millions of nodes and millions of edges. Yeah, and so we labeled these anomalous edges in Huawei with the help of the experts. And so here I have graphs showing the temporal distribution of the datasets to give you a deeper idea about the datasets. And yes, so you can see that on the x-axis, we have the hours, right? And so the duration is approximately 10 days. And these different peaks, they correspond to the daytime, right? Because there's more activity during the day. And we divide the data sets in a train and validation and test sets based on where the cyber attacks are present in the data set. So we want to put all the cyber attacks in the test set. And so that's why this dashed line, yeah, basically corresponds to these splits. Right. And then you can also notice that, like mainly in Thea, there is a big gap of low or no activity. And the same is happening here at around the 240th hour in trace. And so this is because when the data was originally collected by DARPA, the audit logs, they had some problems with the machines, and so they had to reboot the machines, or they didn't notice that the machine wasn't recording certain events. Right. And also in these graphs, you can notice that we have orange and blue color. There's also gray, but yeah, so gray is very low. I don't think you can see it. But so gray basically show us how many edges are repeated. So meaning an edge between two nodes, whether we have seen this edge at any point in time before. And right, so there are not many. But we have seen unseen, meaning that one node we have seen before, and then the other node is completely new. And then for orange, we have unseen unseen, so both nodes are completely new. And yes, so the edges are not repeating that much. So this also speaks to the difficulty of learning on these data sets. But given that the majority is still in this seen unseen category, so we believe that doing learning still makes sense. But we also think that node features are important in this setting. Right. And so that's why when creating our method, our first step was doing the node feature extraction, which I'll describe on the next slide. But here I'll also talk about the architecture. And so we make the choice of the architecture because we wanted it to be inductive, to handle inductive learning, right? Because there in the test set or validation set, there can be nodes which we didn't see in the training set. Yeah, and we want an architecture that would allow us to handle irregular time steps, right? Because the that's the setting that we have, that the event can happen at any time. And yeah, we frame the problem as a self-supervised link prediction with negative sampling. So the anomalies would hopefully correspond to these negative samples. Right. And so for the node features, so okay, we have three types of nodes: files, sockets, and processes. And so we encode these node types as one-hot encoding. And then we also have 27 edge types. So we do the same for these edge types. And then specifically for the nodes, we also have some other features, but they are all categorical. So we also encode them like one-hot encoding. And so for files, we have their root directory. And so there are 10 different root directories on Linux usually. And so we encode them as one hot. And then we group the files based on their extensions. So we, with the help of experts, right, we look at the different groups that files can be in. So images, executables, documents, etc. And yeah, we have an encoding for each of these groups. Then for sockets, we have three categories for the IP address type, whether the IP address is private, public, or whether there was some error during collection of the data. And for ports, we encode some very common ports like 443, 80, or 22. And the other ports, which are not so frequent, we just divide them into these three intervals. And so then in total, we have 13 different groups. And for processes, we encode the most common process names that were in the training. So this usually corresponds to the system programs like remove, ls, and so on, but also Firefox. Yeah. And now, going into the evaluation, we compare against static baselines because most of the cybersecurity literature, they frame this problem as a static graph. So then after the whole period of time, they just treat the whole graph as a static graph. And so yeah, we use MLP, RGCN, and GAT as baselines. And we also perform an ablation study on whether the including node features is useful and whether using memory in the TGN architecture is useful. And then we also extend the TGN specifically for directionality, because in the TGN architecture, the directionality of edges is only encoded in the memory, but the graph embedding part, graph aggregation part doesn't take the directionality into account. And so yeah, we have these two extensions where OHD is one hot encoding of the direction, and this dear TGN is where we have one graph neural network per direction, basically. So for each node, the information will be aggregated for incoming edges and outgoing edges separately. And then we also do extensions that account for the heterogeneity of the problem. So there are different types of edges and nodes. And so this hetero-TGN basically has one graph neural network per each triplet of types. So if there's the source node type, edge type, and target node type, right? So this is a triplet, and there's a graph neural network for each different triplet. And HGT is a heterogeneous graph transformer. So it's inspired by this paper from 2020. And for all these methods, we use a type-aware negative sampling strategy in the ratio 1:1. So for each positive edge, we sample randomly one negative edge, but we keep the source node the same. We only sample the target node, and we keep the same type, the node type for the target node. And so we evaluate these architectures first on the length prediction. So here we don't have any anomalies yet. We only use the negative samples. And yeah, so we basically want to compare between the static setting and the continuous time setting where we have TGN. And then, okay, we have these two symbols which show us that the architecture is not using any memory. And this symbol shows that the architecture is not using any node features. And so we can see that in general, this continuous time setting performs better compared to the static setting. And then also, if we look at the memory, so the architecture in orange are the architectures that use the memory. And if they are compared with their other part, which don't use memories, right, like one line above, then they always perform better in both cases. Oh, well, in the second case, they perform the same. But this means that the memory helps, but not so much when there are features present. And yeah, and so as we expected earlier, like the features work really well. And so they help the TGN architecture on both data sets, basically, right, to perform better than not having the features. And yeah, and then for the extended versions of the TGN. Oh, yes.
Just one quick question. I think I missed this, but the features that you have are for each timestamp, or they're just initial features?
The features that we have are for each node. So
and for per timestamp, or they're just one set? I want to actually see whether the features are evolving or modifying or changing over time.
No, they are not changing over time.
Okay, thank you.
Yeah, and so then the TGN extensions for the directionality and for the heterogeneity, in some cases they perform better, but in some cases they perform worse. I mean, Trace and Thea. And so like, yeah, the conclusion is they don't really consistently help the performance. Okay. And so here we have the performance on the anomalies themselves, like the labeled cyber attacks. And right, basically the performance corresponds to the previous slide. So TGN and the continuous time setting again has better performance than the static baselines in terms of the area under the curve. And surprisingly, also the extended TGN to directionality and heterogeneity, they also perform quite well. But what the experts care about, right, is the true positive rate and false positive rate. And yes. And so in terms of true positive rate, right, the architectures detect about 50% of the attacks, and they have the false positive rate around 3 to 5%, which can still be improved upon.
So, so just to ask a quick question. So for evaluation here, you also use negative samples, right? Because your ORAG is not computed just on the positive, right? It's on the actual, like how do you actually compute the AUC, for example?
Yeah, so we don't use negative samples here. No, this is just the anomalies and then the edges, like the actual edges that exist. Okay, so positives here are the anomalies.
Okay, so you wait. So just to check. So you only evaluate on the edges that are anomalies and no other edges, but then you will just predict one for all of them, right?
No, like we consider, right, like the anomalous edges are like edges that are not supposed to exist.
Right.
Right. And so we have a test set of edges. So these we call the negatives.
Uh-huh.
And yeah, and then we have the positives, which are the edges that are not supposed to exist. But they are not the negative samples, but they are the labeled anomalies in this case.
Okay. So you have the positives. Let's not talk about positive because I think it's confusing. So basically, you have your anomalous edges as class 1, and your normal edges that do exist in the graph as class 0, or class
Yes.
the negative class.
Yes.
And then you do not train the model either on the anomalies. You just apply it
Yes.
to see if the model can differentiate the normal edges from the anomalous edges that you do have.
Yes.
Okay. I think that's clear now. Thanks.
If I may, I also have another question. Sorry if this is evident. How can you not have a heterogeneous graph in this scenario? Because aren't there 3 classes of node?
Yeah. But it just depends like how you account for the heterogeneity. And so in this normal TGN, without heterogeneity, we would only use the type of the node as a feature.
Oh, okay.
But the heterogeneous architecture is so there's like a whole graph neural network per basically a type.
Oh, I see. Okay, thanks.
Cool. Yeah, so yeah, that's all. Thank you. And yeah, I'll take more questions if you have any.
Right. Can you just go back to the previous slide?
Yes.
So the true positive rate here is the percentage of time where you actually get the anomaly correctly, right? So
Yes.
it means that TGN is actually worse at getting the anomaly correctly than MLP or a GET, which ignores time completely.
Yeah.
So it means that the anomalies are actually not somewhat time dependent, but just structural dependent, because the GET and RGCN doesn't have any information about the timestamp of the edges. They only care about the graph structure, which you flatten it out as a static graph. So it means that it's actually, for this task specifically, it's actually better to use a static graph approach.
But then like your false positive rate is really high, right? So that means that
Right.
like MLP would label, okay, not everything, but like 1/3 of all the edges that you have. And then GET would label like almost everything as
I see.
as an anomaly.
Right. So I guess in the practical use case that you are aware of, which one of these would be if you have to rate these methods, which metric would be the most important, I guess? Or you should take an F1 score of the true positive and false positive rate or something like that, or harmonic mean or something.
Right. So I mean, so it really depends because like we are labeling it on the edge level, right? But each cyber attack consists of multiple anomalous edges. And so you would like to get, right, like at least one or at least a few edges for each attack. And so in this case, like even though we can detect only half of the edges, we detect all the attacks in all of these cases. So yeah, so then FPR becomes the most important metric, because right, if you have a lot of false positives, that means that like the cyber security experts who will look at these results, they will have to manually check also all the false positives, whether they are like real cyber attacks. And so like even if you have like 10 million, okay, if you have 100 million edges, right, then 3% is still a lot. Yeah, so
That makes sense. Right, thanks. So I do have more questions, but for those in the audience, feel free to interpret and ask other questions as well, or type in the chat, whatever way you prefer. So I was thinking that usually, so I've worked with anomaly detectors like before, and I've seen some classical methods that are non-CNN based. They usually make assumption about what the anomaly is about, usually assuming that it is a certain burst of edges. So you have a large concentration of edges at particular timestamp, and that will in general be the hypothesis for like anomalous attack. So so in your model design, I think you pre-train with the link prediction. So what do you think is the underlying assumption you have about the attacks, and like, you know, how does it connect to like with the training that you are doing?
right. Yeah, so I mean, in this case, like cyber attacks are usually not bursts of edges, so we didn't want to make this assumption. But yeah, when talking about the negative sampling, then that means we are assuming that the edges, like the malicious edges, are somehow out of distribution, right? That we have not seen them during training. And given that like the features are very important, tells us that, to a certain degree, maybe the temporal part is not that important, because we can detect some of them based on the features. And then the temporal aspect might like mostly influences the fact that like if you aggregate all of the edges after some time, there is a lot of edges for each node. So then you have to aggregate a lot of information, and this creates a lot of noise.
Right, which leads to the higher false positive rate. In a
Yes.
sense.
Yeah.
Okay, that makes sense. There is one question from the audience. Feel free to unmute yourself to ask as well. But what do you recommend can be done to further reduce the false positive rate?
Right. So like the false positive rate definitely has a lot to do with the negative sampling strategy, where you could also make further assumption, but so we only did we only did 1-to-1 ratio and just completely random sampling. But if you have some knowledge about what the anomalies look like or what their distribution could be, right, you could implement this somehow in the negative sampling strategy.
Right. That makes a lot of sense. Yeah, so thanks for sharing this very interesting work, I think, and also the data sets. I think it's like very beneficial for the community and for people to try out different temporal graph models and see what happens. I think another limitation potentially is that, so I think you talked about this before, but the data sets are also very noisy, right? The edge distribution, and also you have the server that's not turned on and so forth. So it's also, it might be difficult for the model to actually learn the correct behavior of the network, assuming that it's not, there's some discontinuity in the data stream and stuff like that, right? So yeah, so I think in the future with potentially like larger data sets, like 100 million or something, potentially you can learn a very strong model that can you know kind of understand the underlying distribution better.
Yeah, definitely. I mean, we released the code, and we also provide a way, like a simplified way, how to visualize and how to label data sets that are basically collected the same way that these two data sets were. And yeah.
That's very interesting. And is there any like future work that you are planning for now?
For now, no, because I started working on something completely different, but I still think that there are many interesting directions that like this could lead into.
Okay. Yes, definitely. Sounds good. Yeah, so if there's no more questions from the audience, we can wrap up the talk like for today, and then I think I will see you guys back for next week's reading group. Yeah.
Cool. Thank you.
Thank you for the presentation. Let's thank the presenter for the presentation again. Thanks.
Excellent. Thank you.
Thank you.
Thank you.